Hi there everyone, lesson 9 UML guide. So what we're going to do now, and this is going to be something that carries on for several lectures, probably at least another 10. We're going to go through UML. Now the problem with teaching UML is that you have to have data to back it out with. You can't just do it in kind of theoretically. Regardless though, I'm going to try and do it theoretically for as long as I can. And one of the approaches that I thought, and this is actually probably quite unique, is that I wanted to actually teach this stuff with propositional logic as well. Because one of the problems is when you learn this stuff, you don't really learn propositional logic, and propositional logic is something which has been around for many thousands of years, and we went through many different types of reasoning before obviously modern predicate logic, first order predicate logic came along. But what we're going to do anyway, I'm not going to get too much into that. It's probably something from when I'm a bit older I can think about these issues in more depth. However, most important thing to start with, and I've got my highlighter out so I can tell I'm serious. Deductive argument is valid argument. Okay, that's what you need to know. That if it's argued deductively, it's valid. It's not. You can't go back and say anything about it. Okay, deductive argument is valid argument. Make sure you know that. And valid arguments are referred to as deductively valid arguments. So the premises of a valid argument imply their conclusion. Okay, so once we know the premises, the implication, is the conclusion. Therefore, the conclusion is deducible from the premises. Okay, and then we have to remember that induction is the hallmark of scientific reasoning. So, this is observation statements. This is when you're doing an experiment in the lab. You observe stuff, and and then you make some inductive arguments about it. Okay. Inductive arguments go beyond the content of its premises. So you have to remember that we don't know really what kind of unless it's the perfect experiment with all the perfect characteristics. An inductive argument is making that leap, isn't it? It's the scientific leap of discovery. But still, it follows logically. You're not just making that whatever the fuck you want, are you? And now this is really yeah. I wrote this bit myself. No, I wrote actually quite a lot of it myself. Obviously, I was using a lot of sources though. Induction is the front line, the research project, the new breed. So deduction is the back end, the old guard spreading to the masses. So in general, this is what happens. All the scientists and the top people, the smartest people, they go out there, they find out stuff, and when they get older, they decide, to try and use their knowledge to spread it to more people. So, obviously, I suppose I'm young, so I'm not that young. To be honest, I'd like to be as older. I wouldn't like to be older quicker. Luckily, you don't really get much choice in that. But yeah. The thing about deduction is you've already got all the inductive argument. You're adding to the great history of mankind at the deductive end. Whereas induction, you're just you're playing around with some new 20 nanometer material or something. But with deduction, you're dealing with thousands of years of fucking knowledge. Yeah, deduction is real knowledge. Deduction, it's the real hardcore knowledge there. Okay. An argument is valid if and only if it's an instance of a valid logical form. Yeah, so these things have been decided already, basically. Propositional logic. You have to have the right form. You have to have the right if. You have to write. An instance of this and this sort of stuff. If you don't know what I'm talking about, you don't know anything about logic. I don't know why you're watching. So it's not my problem. Anyway, formal logic constitutes a set of rules and standards. Yeah, that's pretty okay. Ideals of inference or norms done normatively. Normatively means prescriptive as opposed to informatively, which means descriptive. I can't change that because I'm in highlighter mode. There's no way to get out of it as far as I can tell in this Windows journal program. But yeah, so normatively means prescriptive. Let's try and get a bit more accuracy on the highlighter pen. As opposed to informatively, which means descriptive, yeah? So prescriptive, you're basically saying you're going to be talking about system flow. You're going to be talking about how things work in a very delineate, in a very kind of clear, precise, algorithmic manner. You're not describing it. This is not something which is it's not descriptive language. That's something else. This is prescriptive. Okay, so their opposition is very, very much binary in nature. The modal definition of validity: an argument is valid if and only if, whenever its premises are true, its conclusion must also be true. So if you've got two correct premises, then the conclusion is going to be true. And then we have a perfect valid argument. So yeah, that's some of the basics of the different kinds of logic. I mean, really, this point here that I wrote is very important. This section. Just change the color. But anyway, yeah, that section is very, very important. Now, what I wanted to do was to look at some of the kind of team players we need in our team. I'm not going to lie, I don't really want any team players in my team, so they can all fuck off. But beyond that, there are some people out there that actually like to interact with other human beings. So, if we're thinking about making teams and stuff like that, you need to think, what is your team role contribution going to be, and what allowable weaknesses are there? Obviously, you're kind of coming from this as the boss, I suppose, and this is just a way of dealing with little fucking kids. But oh well. I haven't really sold it to you, have I? But it does make sense. I'm sure, this is, if you're a complete fucking dumbass, even you will understand this bit. So, anyway, the plant is creative, solves difficult problems. The problem is, loses touch with everyday realities. And spelled out fucking wrong as well. Resource investigator, enterprising, quick to explore opportunities. So yeah, he's very explorative. We can follow through. Great. Coordinator, makes good use of group activities. Problem is, they're manipulative. Shaper is driving and challenging. The problem is they're proactive. It's kind of funny, it almost does sound like it. Vocative. Anyway, yeah, they're provocative and aggressive. Yeah, complete finishers, painstaking, conscientious. So they're anxious, they're reluctant to delegate. A team worker will be cooperative and doesn't want any problems. Problem is they're indecisive. Monitor evaluator is discerning and objective. They're uninspiring and slow moving. Implementer is disciplined, efficient and practical, but they're slow to see new possibilities. And the specialist is single-minded, professionally dedicated, but limited in interests. So if we look at it like this, we can see there's three kinds of role that you can have. You could be a shaper, an implementer, or complete finisher. So, I can actually think of using my pen for something useful now. Shaper, implementer, complete finisher. So these are the action roles. Let's just put that. Shaper. Oh, you fucking Shaper, implementer, complete finisher. Okay. Yeah, I'm sorry about this kind of lack of professionalism in this lesson. But the problem is, you have to, the whole point of business practice is about lack of professionalism. So obviously I'm actually talking about proper computer stuff. I don't know, maybe I'll find that somehow they're linked. I'm sure they are linked, they must be. I mean, human beings invented computers. Computation is just an art form, not based on the actual, actualized reality. So I'm sure there'll be no problem. So yeah, so there's shaper, implementer, and complete finisher. So, and that, yeah, provocative and aggressive at the top there. Anyway, so you can see the other ones: coordinator, resource investigator, and team worker. enterprising, makes good use, and teamwork. You can see how this sort of works, can't you? Plant, monitor, evaluator. Yeah, plant and monitor, evaluator are probably the most important people to, because they're the smartest. No. Oh, yeah. I don't know. It depends, doesn't it? I mean, Hennessy, who wrote the book, Computer Organization and Design, as well as a book on computer architecture, and he was instrumental in bringing MIPS. I don't know. It'd be interesting to think about what he might be. He may not be one of those two, actually, but that's something for another time. Anyway, we said we're going to talk about UML. We haven't even got to it yet, so we're going to get to it now. I mean, this is not going to be that much on UML. There's going to be another few lessons where I'm going to be going off on UML. But what I'd really like to do, and it's the way I even write my notes, so it's going to make more sense if I just give you this kind of blend, of propositional logic, stuff with databases, stuff with Java, and there's no real point. And this is one of the problems with having like just one course. It makes more sense to actually unify courses or things like logic, and I'd prefer it, to be honest, that maths and computer were the same subject really, if I'm really going to go into it. But that's it should be really. I don't see the point of learning maths without learning computers. You're just going to learn applications and differentiation anyway, aren't you? Differentiate. Yeah. Anyway, let's move on to this. First rule of computer science, don't think about what you don't need to think about. So I'm breaking that rule, aren't I, a bit? Anyway, UML is a general purpose modeling language in object-oriented engineering. And obviously, like we said before, we even said it in lesson 4, I believe, on one of those 42 points. We model objects from a problem domain. So if we've got that domain, you can think of it as a place, or best to think of it as a place. There's going to be problems in there, aren't there? Because we don't know how the fuck to model it. So universities, we're going to have loads of problems. Fucking student, course code, billing, all these fucking objects are causing problems. So, and they're all and it's all to do with that one domain, that one place. Yeah. Same for a fucking pet shop. You need pet food objects, timetable objects, administration objects. You need all sorts of shit, really. I mean. And then we might derive, we might have a student object with all the whole form out there, with all the fields and stuff, and then you want to put in the bits, but you're going to need these are going to be, you need a proper student object, that's going to, be super on it, and so all the other things can come in, and like, I don't know, mate. I don't know. If you've got a certain student like John, Peter, I can't think of any more interesting names that will interest you. That's it really. You got to have those student names separately. Same with course code. You might only want to apply all the certain students to each of the courses. So we got it depends how many people you want in each course. You need to be able to build that top level structure, don't you? So you can just plonk people in from one and then to the other, and once you build this structure very nicely, and you try not to get too, you try to make sure it's not fucked up, then you're laughing basically. There's two main types of diagram in universal modeling language. There's behavior and structural diagrams, and these things do very different things. Behavior is really to do with what the fuck is going on here. Use case diagrams, activity diagrams, state machines, sequence diagrams, timing diagrams. These are all very important types of diagrams, and we'll be looking at them next time. We'll especially be looking at use case and activity diagrams next lesson. And these there's a lot of terms you're going to need to learn about them. Ones I will tell you to learn right now are actor and control nodes. So if you know what actors are and you know what control nodes are, you're going to be okay with the next lesson. If you don't, I advise you to have a little look at it. When I take you through the next lesson, you'll understand it better. Now, structural diagrams. That's how it's built. So we need to be really drilling into it now. This is internal shit. Yeah, this isn't just fucking. This isn't something that your proxy fucking user can understand. Yeah, you need to be a fucking pro. Yeah. So it's how it's built. We need to deal with the component, class, the composite structure, and the deployment. Okay. So, and we'll be moving on to them as well. What else have we written? This is a semantic data model where we define the meaning of data within the context of its interrelationship with other data. So with semantic data models, it's all to do with interrelationships, as in fact propositional logic is, first order predicate logic is, and I suppose electronic logic. There's many types of logic when you really look into it. Lots of other abstract ones that I haven't covered. So we look at things from top down, not bottom up, and that's so important to understand that the way that everything works is top down, not bottom up. So even though you need to learn things bottom up, you have to integrate them. And this is something I've mentioned before. You have to integrate the bottom up learning into a top down framework of information gathering, brain gathering, I suppose. This is how progress is achieved. Because if we kept on going bottom up, then, you know, it would just have adults acting like children all the time. It's similar to the Chinese system. I didn't fucking want to do that. I didn't want to slack with the Chinese even here. You know, but I guess it's real. It's reality, isn't it? It's fucking reality, mate. Fucking simulacra principle, all that. Anyway, so we integrate relational database techniques with abstraction found in our artificial intelligence. I'm probably not going to go in too much into artificial intelligence, purely because it's actually what I like to do, and I don't really want to help you guys out with it. Yeah. Don't know, maybe if I get some fucking decent subscribers instead of a load of faggots that keep subscribing to me, then you know, I might be inclined, you know, to actually talk in more depth about these issues. Yeah, so watch out some of these acronyms: ICAM and IDEF. ICAM is Integrated Computer Aided Manufacturing. That's the 1970s, a high initiative to integrate manufacturing into modern age, going beyond the monolithic function. So that's always been traditionally how manufacturing has been viewed. And this is, you know, trying to bring this cognitive analysis or whatever it is to the, you know, manufacturing. Whether that makes any fucking sense or not, not going to lie, probably I doubt it. Anyway, integrated definition. That's a government project to formalise definition. That's a bit more interesting, actually. They're both quite interesting, though, you know. And this is basically a way that, you know, kind of business types who are kind of dumbasses can find a way to stop computer scientists getting too pissed off. That's basically how that works. Oh yeah, there's one other thing I wanted to cover, which is a couple of tenets of Java. It's not a good way to look at it. As you'll notice, the first letter of each word here spells out a pi, which is, yeah, that's good, isn't it? So, 1, 2, 6, 5. I always get lost about it. It's probably because of how many digits a calculator can show. Let's just leave it there. Anyway, abstraction, polymorphism, inheritance, encapsulation. With basics of object orientation. You know, it's a bit like orienteering. Orientation. Orienteering is actually a very... Abstraction is a way of looking at something or viewing something. So, a car is an engine, and the concept of engine is an abstraction by definition. Engine is a generic word, and it's a high-level look or description, and that's hidden from the user. Don't know the subunits of engine, but I know what it does, so I don't need to think about it. And that's another way that I was telling you about something before, isn't it? We don't talk about the internals if we're just looking at the external function. There's abstract data types, a queue, a stack. These are some more advanced data types that arise from, you know, concatenating arrays with variables, etc. Okay, polymorphism. Something is polymorphic, it can change or adapt. So for instance, Odo from Deep Space Nine, he's a shapeshifter. If there's a tiny crack in the wall and he needs to get through it, he wouldn't just walk in straight in there because he'd be a massive bloke and the crack is tiny, so he would you know, morph into some amorphous substance. Will I use that textually correctly? I will find out afterwards. So it can be a physically existing object or something that doesn't really exist, like an invoice or print object. It's very common in history. Might take a printout character on a screen, might print out an image or an email file. It can adapt to whatever input we give it, so it can adapt according to its environment, so it can morph into whatever we want it to be. Yeah, I'm sure amorphous. Yeah. And there's another thing, isn't there? There's opaque, transparent, translucent. You know the difference? Let me know. I know the difference, but you probably don't. In fact, I know you don't. Okay, inheritance, hierarchical structures. The Java structure all work through inheritance. So user procedural is not how it works. All right. And encapsulation is often called information hiding. We'll be talking about this later on when we look at networking in Java. Okay. Anyway, so I mean, I hope you kind of appreciate some of the things I've gone through today. Obviously, we've looked at a few different things. We're going to be getting very heavily into MIPS as well soon, and so I'm going to need to talk you through some of the stuff that I've been doing at the moment. So yeah, as you can see, this is a bit of a mess, but action roles, P roles, thinking roles, and then it's all good stuff though. This stuff I'm taking you through, and I hope that the way I've chosen to start it is a way that I really felt very strongly that this was the way to do it, to start, to start things this way. This is kind of the way that I wish that I'd started with, kind of computer science, because once you understand induction and deduction, and make sure you understand what the difference is between the two. Yeah, I can't stress that enough. Because then it's not completely clear that that induction, once it goes into deduction, is not. The process of it going from induction to deduction is quite difficult. It's when does that become complete knowledge, as opposed to someone. It's like you can imagine, like, if someone said London is the capital of UK, but you're back in like the 16th century, it probably wouldn't really be knowledge, would it? Until you really know it, until there's thousands and thousands of people verifying it. And in the scientific framework, it's even harder than that, because you actually have to, because the verification is so much more stringent, and it's not something which is, it's not just like, it's a more complex fact, isn't it? And the complexity of facts lead us to struggle to put these things into deductive boxes. But we have to put them in deductive boxes so that then further induction can occur.